Good afternoon, all of you. So today we are starting with module 3. So what we are covering in module 3 is mainly the high frequency response. High frequency response of MOSFET circuits. Okay. So in that first we will cover what are the general aspects of high frequency. That is why we are going for high frequency analysis. Till now we have discussed a small signal equivalent circuit and the parameters, right, in module 2. Common source, common gate, and common drain amplifiers. We have been discussing the small signal equivalent circuits, and through the analysis, we have derived the performance parameters like input resistance, output gain, uh, overall gain, all those things. But now we are going for the high frequency response. So in general considerations, we will be discussing why we are going for the high frequency. So what is the significance of high frequency response? So from that, there is one important parameter which is called as high frequency gain function. So how to achieve this particular equation, or by seeing this equation, what are our implications? Okay, what are our inferences? All these we will discuss. Then you might have heard about 3 dB cutoff frequencies, right? And you know the importance of 3 dB frequencies in lab experiments. You have done practically how to find the 3 dB cutoff frequencies. After finding the frequency response, you will plot the gain versus frequency log f. Then from that you will actually uh, achieve the 3 dB cutoff frequency. But here, analytical way how we are finding the 3 dB cutoff frequencies of the circuits by using open circuit time function method. That is the third part. Then we have the high frequency response of these amplifiers, CG and CD. CD is otherwise called a source follower. So all the three configurations will be discussed in detail with active loads. So I'll be telling what is the purpose of using active loads, or how we can load this amplifier for biasing. And from that we will calculate the frequency response as well as the cutoff frequency. Okay, cutoff frequency is very, very important while designing the amplifiers. So for all the configurations, we will derive the cutoff frequency for both CG, CG as well as CG amplifiers. Then next we will discuss about the cascade amplifier, the basic fundamental circuit of a cascade amplifier, and what is the frequency response of this cascade amplifier, how it will differ from the conventional amplifiers that you have discussed in CS, CG, and CD. Then coming to the different versions of cascade, double cascading, folded cascade, bi-CMOS cascade, cascade current source. So these are all the different versions of cascade. So this is the content of module 3. So let me explain once again. First, we will discuss about the high frequency response, including the general considerations, high frequency gain functions, and how to determine the 3 dB cutoff frequencies. Then we will discuss the high frequency response of the three configurations, CS, CG, and CD amplifiers. Then another configuration, cascade amplifier, and different circuits coming under cascade amplifier. So first, let us have a brief outlook on high frequency response and its general consideration. So if you take a direct coupled amplifier, what do you mean by direct coupled amplifier? Without using capacitive coupling, directly we will couple the input and take the output. Normally, in the previous classes and all, we have discussed the CS, CG, and CD amplifier analysis, small signal equivalent analysis. In that, we have considered the coupling capacitors CC1 and CC2 at input and output. Basically, they will act as a coupling capacitors, right? So, unlike the capacitive coupling circuits, we have another versions of coupling, that is direct coupling. Direct coupling means we have a direct connection between the signal source as well as the input terminal of the amplifier. Similarly, the load will also connect directly with the drain terminal without any capacitance acting in. That is what is called direct coupling amplifier. So whenever we take a direct coupling amplifier and analyze its frequency response, This will be the graph, right? So this is called as a frequency response graph. So frequency response is nothing but the plot between the gain and frequency. So in the x-axis we are having f, in the y-axis we are having mode A. So modulus of A is nothing but the magnitude of gain in decibels. Okay. So initially we are having the maximum gain. Okay. Initially we used to have the maximum gain, but what we can observe is after a particular frequency fh, our gain will start decreasing. This fh can be called as 3 dB cutoff frequency. Now, how we have achieved this FHS? With respect to maximum gain, we will subtract 3 decibels because this is already plotted in decibels. I have converted the gain into decibels by taking 20 log. You know that gain is a dimensionless quantity. So whenever we want to parameter or characterize this gain in some way in a particular scale, we have to convert into decibels. So for that, we are using this conversion technique 20 log mode AM. Okay, where AM stands for mid-band gain. Take down the lecture notes. AM stands for mid-band gain. So the mid-band gain constitutes the maximum value. Okay. But later, after a particular frequency, it will start decreasing and we will find the 3 dB gain, means the gain corresponding to 3 decibels subtracting from the maximum gain. That is what is called 3 dB gain. So from the maximum gain, we will subtract 3 decibels and correspondingly, we will mark the frequency. That is what is called FH or 3 dB cutoff frequency. So this is a general way of representing the frequency response graph of an ordinary amplifier. So here you can see that the gain is remaining constant for a while. So that constant gain, which is of maximum value, that is called as mid-band gain. Okay, mid-band gain, which is represented by AM. So it is evident from this figure that for low frequencies only we are having what? Maximum gain. The low frequencies are nothing but closely approximated as DC. Isn't it? Low frequency means DC, high frequencies is AC. So this AM is nothing but the actually the gain that we have achieved for DC inputs. Okay. So what is the word meaning of frequency response? Frequency response means how the circuit is responding towards various input frequencies. Isn't it? Response means output. So how the output of the amplifier or gain of the amplifier is getting varied according to the changes in input frequency. So we are having maximum frequencies for low, maximum gain for the low frequencies. So this low frequencies can be actually treated as DC. Therefore, DC is nothing but the zero frequencies. So for zero frequencies, we have a gain which is remaining a constant and it is called as mid-band gain represented as AM. So whenever we are dealing with a direct coupled amplifier means without any capacitive coupling, we will always experience a constant gain for a wide range of frequencies. Sudden fall of frequencies is not experienced in a direct coupling case. Okay. Whenever we use capacitive coupling for the input and output cases, in that case, your gain may decrease advance. Okay, that is for low frequencies itself, you can see that decrement in gain. But for direct coupling, it is observed that for a wide range of lower frequencies, your gain is maintained substantially constant. Okay, so the advantage of direct coupling is that they do not suffer any gain reduction at the lower frequencies. But still, you can see at higher frequencies, they do experience some sort of gain reduction. So why that is happening? That is, even though we are not using any external capacitors for coupling purposes, but still we do have some internal capacitances across the transistors, that is MOSFET's junction. Okay, transistor here means it is MOSFET only. So basically in microelectronic circuits, we are considering MOSFETs rather than BJTs. So internal to this MOSFET or transistor terminals or junctions, we do have some sort of internal capacitances presence. That is what is called junction capacitances. For example, we have the capacitance between gate and drain. Similarly, we have the capacitance between drain and source. Okay, and gate and drain even. So these capacitance are contributing towards that gain reduction. So how this gain is getting reduced, that is because of this kind of phenomenon which is called as charge shortage phenomenon that takes place inside the capacitor. Okay. So the capacitors are exhibiting some charge shortage phenomenon that takes place inside the capacitor. You can take down that point. Charge shortage phenomenon which is exhibiting in the internal capacitances of the MOSFET device. So why that charge shortage phenomenon is happening? Because at high frequencies, normally the capacitance will have low reactance. As you know, the expression of the capacitive reactance, right? X is equal to 1 by 2 pi Fc. Basically, the capacitance will allow high frequencies. Capacitors have the tendency to allow high frequencies to pass through and attenuate or block low frequencies or DC. That is why capacitor is a charge storage device. Charge storage means it is blocking DC and passing AC. So for high frequencies, what is happening is that capacitance will have low reactance. Xc will be less, right? Xc less means it allows a conduction of AC current. So basically, this act of short circuit, the two capacitive plates. Okay, even though we are not connecting physically the capacitance in the circuit, but still due to the internal capacitance, the circuitry, that is due to the internal capacitance or due to the presence of junction capacitances, the capacitors will appear as short circuit. The two plates will be shorted together, and because of that, the charge shortage phenomenon is taking place. So this will decrease the gain, which will reflect at the output also. So the amplifier gain, taking into account the internal capacitance, can now be represented as a function of complex frequency variable S in the general form. A of S is equal to AM into FH of S. So you can write this expression. So this expression, all of you please listen, this expression is nothing but the equation for amplifier gain, which is a function of a variable called S. This S is nothing but the complex frequency term. So we know that if you take any amplifier, even though it is a direct coupled amplifier or a capacitive coupling amplifier, but still we are experiencing a non-uniform gain. Even though till FH we are having constant gain, and thereafter we are experiencing a drastic reduction in the gain. So what we can write is the gain is always a function of frequency rather than writing simply AH. A means it is a constant, right? Whenever you are representing capital A means it is a constant. But while you're representing A of S means it is a function of S. That means whenever S changes, gain also changes. So this gain is a function of frequency. That is what is meant by A of S, which is equal to AM into FH of S. AM already I have discussed. AM is called the midband gain. That is midband gain means the gain associated with the amplifier till your cutoff frequency. Correct? What is midband gain? Midband gain is the AM. The gain of that amplifier till your cutoff frequency. That means that constant part that is called AM. So that is multiplied by FH of S, where FH of S is called as high frequency gain function. Please note down the equation as well as the parameters names. AM is a midband gain and FH of S is a high frequency gain function. So actually this high frequency gain function is determining our A of S for different values of S. S is nothing but a representation of frequency. Okay, it is a complex variable. Whenever we are plotting the frequencies in a complex plane, we used to go for the Laplace transform. That Laplace operator is called as S for analyzing a continuous time domain system. Just like set transform, which is applicable for the discrete time system, Laplace transform is applicable for a continuous time system for its analytical purpose. So here you can see fh of s is the high frequency gain function which has got some effect over a of s. So how we can find am? Am is a constant. That constancy will come only for low frequencies, right? Till fh. So low frequency means xc will be high. Xc high means the capacitance act as open circuit. So when considering all the internal capacitances as a perfect open circuit, whatever gain we can calculate, that gain is nothing but AM, which is otherwise known as mid-band gain. But after considering the effect of those internal capacitances, then we have some charge shortage phenomenon taking place inside the circuits, because of which your gain is coming down, and that is nothing but your A of S. So whenever you are talking about A of S, we have to take the high frequency gain function into consideration, that is going to alter that constancy. Till that it was AM. But after a while, that is whenever we are taking the internal capacitances into account, we have to multiply this AM with your high frequency gain function so that we get the overall gain. So here it is mentioned that the value of AM can found by neglecting the effect of internal capacitances. Why they are neglecting? Because they appear to be open circuit for low frequencies, because AM means it is nothing but the mid-band gain for low frequencies. So low frequencies means capacitive reactance is high. Capacitive reactance high means they will block the current. That means they are offering infinite reactance, that is open circuit. So whenever all the capacitances are taken as open circuit capacitor, then whatever gain we are calculating from this amplifier, that gain is called as mid-band gain AM. But later, the gain will change depending upon the frequency. That change in gain can be approximated by this particular equation, A of S, which is equal to AM into FH of S, where FH of S is called as high frequency gain function. I hope you have written this. Now let us discuss more detail about this FH of S. After taking the capacitances into consideration, the gain will multiplied by FH of S, or gain will start reducing by a factor of FH of S. Suppose FH of S is 1 by 2. For some reasons, FH of S is 1 by 2 means you can claim that my gain has been reduced to half at a particular frequency S. Isn't it? Suppose FH of S is 1 by root 2, then my gain has been reduced by 0.707 or 70.7% of maximum value. Then we can say that that gain is a 3 dB gain, and the frequency at which I am achieving this particular gain, that frequency is called as 3 dB cutoff frequencies. Understood? So FH of S is nothing but the factor that is multiplying by AM, and it actually reduces our gain by a particular amount or a particular factor, isn't it? So that FH of S can be expressed as this equation in terms of poles and zeros. You can take down the equation for FH of S. So if you have any doubts in the concepts, you can post me and ask. So the equation of FH of S is given by 1 plus S by omega Z1 into 1 plus S by omega Z2, etc. into 1 plus S by omega Zn whole divided by 1 plus S by omega P1 into 1 plus S by omega P2, etc. up to 1 plus S by omega Pn. N stands for the number of poles and zeros. So from this equation, it is understood that this high frequency gain function is nothing but a polynomial, an nth degree polynomial, which consists of n number of poles and n number of zeros. You know that zeros corresponds to numerator and poles correspond to denominator, right? So whenever at a particular frequency, the function becomes infinity, then that frequency can be considered as pole. Now, whenever we are taking one frequency and for that particular frequency, my high frequency gain function is becoming zero, then that frequency is called as zero. Okay. So the frequencies at which the function becomes zero, that is called as zero frequencies. And the frequencies at which my function becomes infinity, anything by zero is infinity. So that frequencies corresponds to poles. For example, if S is equal to minus omega Z1, in this place, if I'm putting S is equal to minus omega Z1, then this term will become zero, because of which our gain function will become zero. Therefore, omega Z1 can be considered as the zero frequencies, ZDRO. Okay, zeros. Similarly, if S is minus omega P1, then this term will become zero, right? Minus omega P1 means 1 minus 1 will become zero. So anything by zero will become infinity. So your high frequency gain function is becoming infinity. In that case, that particular frequency is called as pole. So for what value of S that makes my function infinity, that is called as pole, and the value of S that makes my function zero, that is called as zeros. So now we need to find for what case this particular function approaches unity, means fh of s becomes 1. Tell me the condition when fh of s becomes 1. Fh of s becomes 1 when s is 0. S 0 means zero frequency. Zero frequency means DC. S is a complex notation of the frequency in the complex plane, right? So S0 means it is understood that frequency F is equal to 0. Zero frequency is nothing but DC. So for all the DC signals, you can say that the high frequency gain function will be 1. If high frequency gain function is 1, then basically from this equation, you can write A of s is equal to AM. Is that clear, students? Please respond. Is that clear?
Yes, sir.
Okay. So if we substitute 0 for S is equal to 0. If S approaches 0, all the terms will become 1, right? 1 into 1 into 1 divided by 1 into 1 into 1. So the ratio will be 1 is to 1. So FH of S becomes 1. If FH of S is equal to 1, then A of S is equal to AM. That is irrespective of change in frequencies, right? The AM, the gain is constant at AM. That is what is called mid-band gain. So we can cross verify with our graph at zero frequencies. The gain is nothing but AM. The gain is nothing but AM. Okay. So that is what we have mentioned over here. So for zero frequencies, that means for DC signals, the gain is AM, which is a maximum gain, otherwise called as mid-band gain. Now, how we can determine the 3 dB frequency FH? So this mid-band gain will continue till FH. After FH, we are experiencing a sudden deterioration in the gain. So how to find this cutoff frequency FH? So for any electronic product to design, we need something called as specifications, isn't it? Basically, we will have a survey from the society, analyze the problem faced by the society, because we are working for society, right? So to work for the society, we should be able to give solutions for the problems faced by the society. So generally, before starting any project or before starting any product development ideas, first, that is why everyone is telling, go for the literature survey. The literature survey is nothing but to analyze the problems faced by the society and find out the gaps. Gaps means something which is not getting filled. So fill the gaps by proposing a new system based upon the specifications and constraints. So we have to collect the requirements from the society, what they need actually from us. Being a technical engineer, what is our objective to offer the solution? So for that, we have to collect the requirements from the or feedback from the society. Those requirements we have to convert into specifications. Specification is a word which is actually technical thing, but requirement is general word. Okay, specification is a technical word. Requirement is a general word. So we have to convert the general into technical. So once you get the technical parameter, we have to work to achieve my solution towards that particular specification. So for that, we will constitute the blocks. Blocks have to be interconnected suitably. Each and every block we have to separately analyze, find the components, right, to build that particular block, work on it, give input, take output for each block, identify the error for each block. So if there is no error means it is fine. If there is error or the feasible signal is not coming, the desirable signal is not coming out of a block means we have to work on it. We have to replace the components maybe, right? So likewise, individually, we have worked on each and every small blocks and we got the desired output, and at last we will interconnect all those blocks and finalize our output. Then that can be converted as a prototype. Whatever the product you have developed just now, that can be converted as a prototype, and again you will duplicate 2 to 3 prototypes and test the same thing again and again, whether it is getting the same outputs for much possible number of inputs. You are verifying it is done, so you have validated it, then you can go for product and manufacturing purpose, right? So manufacturing industries will take over that and they will produce the product or generate the product depending upon the requirements from the market. So that is the thing. So any product will always have its own specification. Like that, here we are having one product which is called as amplifier, and basically they need one specification, that is what is called as cutoff frequencies. In the earlier module, we have some specifications like input resistance, output resistance, gain, open loop gain, overall gain, what is that? Open circuit voltage gain. All these were the parameters. The second module we have discussed all these. But now we are discussing one more parameter which is called as cutoff frequencies. So what is the speciality of estimating this cutoff frequencies? We should know what signal we have to give to this amplifier. Till what frequency this amplifier will amplify the given input. We can't give any range of input signals of any frequencies. Why? Because the amplifier will respond only to a particular range. So if you are focusing in the out of range area, how it will work? It won't work. Simply we will get some attenuated signals that is not at all desirable for us, right? So always we have to analyze the cutoff frequency of an amplifier. Based upon that only we will give the inputs. So if you take one product, already the designed product, then we have to find out its bandwidth or cutoff frequencies, and based upon that we will have to give your input. That is the difference between analysis and design. For design, we should need the specification, and based upon the given specifications, we will go for the product development, right? But analysis means they will give the product as such, they will provide the circuit as such with all the specifications. Okay, not specifications, with all the given maybe some parameters like features of the transistor, constructional features from the data sheet, all those things. Based upon that, we have to find the parameters, find the specifications. So it is not like target achieving, whereas design is a target achieving, whereas the analysis is we will just monitor the performance of the product, and we will come up with some numerical quantities, some performance specifications or some performance values. So here also we are trying to determine the cutoff frequency of an amplifier. The cutoff frequency is specifically called as a 3 dB cutoff frequency because 3 dB means it is 0.707 of your maximum gain in dimensionless quantity. If you have already converted the gain into decibels, means it is just equivalent to subtracting 3 from the maximum value, that is fine. But if you are analyzing the gain as a dimensionless quantity without converting into the dB domain, then what you have to do is you have to find the frequency at which the gain is getting multiplied by 1 by root 2. 1 by root 2 is equivalent to 3 dB. That is nothing but 0.707 or 70.7 percentage. So you may ask why we are specifically multiplying by 1 by root 2. Why we can't go for some other factors or some other fraction? Because multiplying by 1 by root 2 with voltage gain is equivalent to multiplying by 1 by 2 with power, because power is V square by R, whereas gain is proportional to voltage. I hope you are getting my point. Power is proportional to V square, square of the voltage, whereas voltage is gain is proportional to voltage. So if you are multiplying the gain by 1 by root 2, it is nothing but multiplying the voltage by 1 by root 2 itself. Because gain is V naught by V, multiplying V naught by 1 by root 2 means it is equivalent to multiplying the gain by 1 by root 2. Therefore, square of the voltage means it will become V square by 2, right? V square by 2. Output voltage square divided by 2, because 1 by root 2 square is 1 by 2 only. In that way, we can say I am actually trying to find half power frequency. Half power frequencies means the frequency at which I am attaining 50% of maximum power delivered to the load. Because till 49.999% it is fine. Or else till 50.111% it is fine. Okay. Below that, it is not appreciable for me. I am giving some input power. I am getting some output power. But that output power should not fall below the 50% of its maximum power. I am expecting maximum amplified power at the output across the load, right? But that gain, I'm not getting sustained gain for all frequencies. After a while, it is coming down. But that decreasing is also fine for me. But till it is 50%, it is okay. Somehow I can manage my load working with that power. But what will happen if it goes below the 50% of maximum value? It is not that much desirable. So we can call that particular frequency called as half power frequency. Okay, so it is highly mandatory or highly desirable to know the cutoff frequency of the amplifier. Why we want to know this cutoff frequency FH? Because then only we will be able to confine our input signal within this particular frequencies. Otherwise, we will give our signal at our own wish at any frequency range, and the amplifier will produce its own response at his own wish, which is not at all desirable for our load, isn't it? For example, if you take a load as a TV, suddenly the fluctuations is happening in your input AC current. What will happen? The load will not work, right? The load will not work. But fortunately, I have an inbuilt stabilizer with my TV or an external stabilizer with my TV. So it is actually boosting my power, output required power, even though the fluctuation is happening, to protect the load from the sensitive variations of your input, isn't it? So that is an extra circuit that is protecting my load. But here we are giving a manual input, which is coming from the, if you are considering an amplifier, we are giving an electrical signal which is coming from the transducer. Transducer is nothing but the mic. to the mic we are giving the speech signal, right? So we have to control the frequencies of the input signal till the cutoff frequency fh. So the transducer should be designed in such a way that the electrical signal produced by the transducer should not go beyond the cutoff frequency. If it is going beyond the cutoff frequency, it will definitely, the power output that is producing across the load will come down below the 50%. Students, are you able to get the concept? Is that clear for you? Can I proceed? So this frequency fh can be denoted as omega h by 2, where omega is the cutoff frequency in angular frequency domain, right? Omega is angular frequency. So if you divide by 2 pi, this is 2 pi, okay? If you divide this angular frequency divided by 2 pi, you will get your cutoff frequency fh. So normally in this module, we are going to determine the cutoff frequency from the analysis of your fh of s. That is your high frequency gain function, okay? So this frequency fh has a large dependent on the pole than the zeros, because if you take the fh of s function, that is high frequency gain function, all the zeros z1 z2 z3 up to zn will either lie at infinity or at high frequency. So they do not contribute, or they have a little significance in determining the cutoff frequency, because fh will always lie at the